Uh, Hello class, good afternoon. Am I audible?
Yes, sir. Good afternoon, sir.
Yes, good afternoon. Okay. Yesterday's class, were you all able to hear? Are you all okay with yesterday's class?
Sir, actually, I joined yesterday evening, sir.
Okay, fine. Nevertheless, what we will do is today, mm, I will just have a quick recap of what we discussed yesterday. Okay, so that should be
Okay, sir.
fine with everyone. Okay, fine. So I am pulling up my PPT and we will have a quick glance as to what we discussed yesterday so that it's going to benefit for them who have joined me today for the class. Okay, right. So, this was the thing that we discussed yesterday. Now, for those of you who are new, who have joined me today for the class, we are starting off with module 1. Okay, and the module 1 is about introduction, and introduction is all about your Verilog, okay, which I have shown yesterday. Okay, yeah, it's all about introduction to Verilog. Okay, I can just share that screen as well if needed. And keep in mind, we will be using 1718 scheme. Okay, 1718 scheme syllabus. Are you all able to see my screen, the PDF, the syllabus copy?
Yes,
Okay. So this is going to be the name of your subject, system design using HDL, and the course code is going to be C43. As of now, we are going to have lecture series, and the practicals probably will be continuing later at a later point of time. Okay, but as of now, we are concentrating on the theoretical point of view. Okay, and we are starting off with module 1, and the name of the module is Introduction to Verilog. Okay, so that is what we will be discussing. Okay, fine. Are you all able to see my PPT screen?
yes, sir.
Fine. Okay. So here, as an introductory, session, yesterday I was telling about the VLSI companies that are involved. And why do we need to talk about VLSI companies? Because when we learn HDL, okay, it means that we are concentrating on the VLSI industry, right? So, if you look at excuse me. So if you look at list of companies available, okay, it can be your Intel, Cisco, Texas, Wipro, okay, many of them, AMD, many of them are involved with actually hiring those students or those learners who are good at VHDL and Verilog. So that's the reason I have put up all these logos of the company who will be actually interested in students who know Verilog and VHDL. Okay, fine. Now here we will be seeing the basic differentiation or basic bifurcation, in VLSI design. So in VLSI design, as you all know, there are two main bifurcations. One is the ASIC and the other one is FPGA. Something that comes in between is called your semi-custom, which means it will have a little bit of ASIC as well as it will have a little bit of FPGA. ASIC is something where you start off from the scratch, you build everything, but then FPGA is something where you just take components over the counter, which means you can just buy them and then assemble them. Semi-custom is something where you build few components and then some of the components are ready-made and these are integrated together. Okay, so which means it's a part of ASIC and it's a part of FPGA. So it lies in between ASIC and FPGA. Now in ASIC, okay, it is called full custom just because we do everything. When I say we do everything, we design everything right from the circuit. What should be my you know channel length, channel width, okay, and everything, okay, everything is been designed. So we start off with full custom design, then we go with CMOS design, then we simulate. Now whatever circuit that we have, we should simulate and check if it's proper or not. If it's not proper, then we can always get back to the circuit, make changes to it, and then re-simulate it, right? So once we get a proper waveform, it's only then we will be moving on to something called layout. So layout is something where you will be doing it in your labs, VLSI labs, okay, where you will be seeing as to how these are using cadence. So in our college we are using cadence software, so you will be able to design each transistor. So once you have the circuit, you can actually put a layout, and once the layout is done, you have certain checks to be done. So these are called your DRC and LVS. If you have a pen and a paper handy with you, you should be making note of this. DRC is nothing but your design rule check. DRC is your design rule check, and LVS is layout versus schematic. Any doubts you can ask me. Okay, can I proceed?
Yes, sir.
Okay. So DRC is design rule check, and LVS is nothing but your layout versus schematic. Now what are these checks? These checks are nothing but, suppose I design an AND gate, okay, and if my circuit that I have opened is OR gate, so it will tell me that the design is different, and the that happens in your LVS, layout versus schematic. So the design is different, which means the layout is different and the schematic is different. Now what is DRC? DRC is nothing but your design rule check. So every transistor should have its own spacing between each transistors. So which means if I have transistor 1 and then transistor 2, there should be minimum spacing between them. So these are called some rules. Now rules change for 180 nanometer, okay, it can change for 90 nanometer, for 45 nanometer, okay. For various technologies the rules does change. Now what is this 45 nanometer? 45 nanometer is nothing but the distance between the source and the drain, which means it is your channel length, effective channel length. So each transistor will have source, gate, drain and body. So these are the 4 terminals, right? So the distance that exists between the source and the drain is called your channel length, okay, fine. Next, after simulation you will have something called post route simulation. Maybe after simulation you may want to make some changes to it, okay. So once you have done the changes, then again you can simulate. So that is called your post route simulation. Routing is nothing but connections. So once the connections are done, you again try to simulate them. Then there's something called GDS2. GDS2, if you have a pen and a paper handy, if you have a notebook with you, just note down graphical data schematic for information interchange, okay. So that's the full form of GDS2. So this will be like a file which will be sent to the foundry. Now what is a foundry? Foundry is nothing but a fabrication center where they will try to manufacture the IC, they will try to manufacture the chip. So once we give this GDS2 file, they will be able to manufacture the chip. So it is like a code, it is like a source code. So once you give this, they will be able to do it, they will be able to manufacture. Now you have something called semi-custom. So between ASIC and FPGA you have semi-custom. Semi-custom, as I told you, it has certain portions of ASIC and certain portions of FPGA. Here also you do have simulation, you do have verification, gate array, stamped cell, which means you are using some standard designs. Here you will be designing gates. So you're combining both. Here you have your STA, static timing analysis. You have your DFT, design for testability. Okay. Then similarly you have your FP, your CTS, DFT, then placement and routing, GDS2 again the same thing, right? So more or less, the flow remains almost the same. Okay. And here you can find FPGA, then your HDL entry, simulation, synthesis. Now I think you would have seen in your labs previously, right? In your HDL labs, in some we simulate and in some we do the synthesis. Now what is the synthesis? Synthesis is nothing but it will have all the information with regards to clock. When is the clock rising, how much is the delay, when is the clock falling, so rise time, fall time, all the information will be available with synthesis. Okay, next is your placement and routing. Okay, then your bit files, and then the final output. So this one we will be using your Xilinx, or even we can use Cadence for this purpose. Okay, you can connect an FPGA kit and see the output. Okay. So this is an overview as to how your VLSI design is exactly bifurcated, right? Okay. So the next one that we'll be seeing is ASIC. Now again in ASIC we have 4 different bifurcations: full custom design, standard cell, gate array, and FPGA based design. So if you go here, ASIC design again has 4 bifurcations. Okay, so full custom is something where you build everything right from the scratch. Everything is built. Okay, so I have put the explanation also here. This approach is extremely slow and expensive. It is only used to design very high performance systems. Now, I think you would have heard of this supercomputers, right? So most of the supercomputers are all custom designed. When you say custom design, it is designed for a particular purpose. So when you want something for a particular purpose, you don't get it over the counter, or you don't get it ready made. You have to do it by yourself, right? So which means it becomes difficult in order to design it, right? So which means it will take time, it is going to be expensive, but performance wise it's going to be very high. Expensive, yes, I agree, but performance is going to be very high. So here you can see performance and cost, they never go hand in hand. So which means if you really want to save cost, you cannot save on the performance also need to be high. You cannot have a low performing device and then pay high for it, right? So which means they are equally proportionate, directly proportionate. So if you want performance, you have to pay for it, right? Next you have standard cell based design. So here this approach is reasonably fast, because most ASICs are currently designed using this method. So what they do is they take few components which are already designed, okay, and most of the things are designed from scratch. Next, gate array. This approach is fast and less expensive. ASIC performance is relatively slow. As I told you, the performance curve from here to here stops or starts degrading. Okay, here you will have the maximum performance. You come down here, the performance is reduced and the cost is also reduced. You come here, the performance is still low and the cost also is low. Here you come, the performance is low, cost is also low, right? So based on performance and cost, okay, you will have to decide which kind of design you will really want to get into. So I was telling you guys regarding the textbooks, right? So I have put up module 1 from which section you're going to get, okay, module 2 from which section you're going to get, 3, 4, 5, okay, all these are the sections from your textbook, right? So you can have a soft copy of the textbook. I'll be sending in the materials in some time. Okay, probably tomorrow or something I'll be sending the textbook. I'll just look into my resources, and accordingly I will share the materials with you. Okay, so this is picked up from second chapter of the textbook for your module 1. Right. So this is something which is relating to your course outcomes. Once you finish the course, what all will you get to know? Okay, you will be able to know the necessity of VLSI design. You'll be knowing how to rectify a syntax error. You'll be knowing how to program CPLD. CPLDs are nothing but complex programmable logic devices, and then your FPGAs. Then you'll be able to translate the design on state machine into HDL program. Okay, state machines, you'd have seen the state machines exclusively in your digital electronics, right? State machines, Moray and Mealy state machines. Then you'll be able to write HDL codes, and then you'll be able to see what is your FPGA hardware, how you can burn or send those codes onto your kit. Okay, so those are your outcomes, right? So the next one is the number of gates. Now many a times, okay, what will happen is, if you see the number of years, okay, from 61 to 90, of course, we are moving on still with your ULSI technology, okay, which is ultra large scale integration. And here you have SSI, small scale, medium scale, large scale, very large scale. Okay, so here it is given which year, 61, 66, okay, and so on. So let us see one by one. In SSI, okay, SSI technology, it was in the year 61, and there were about 20 logic gates. And if an example is asked in the exam or internals, you can mention as flip flop, decoders, and registers. Okay, and then MSI was in the year 66. Now see the jump here, it's about 10 times jump. The previous generation had only about 20 logic gates, but here you will find about 200 gates. Okay, so it's a 10x increase in the number of gates. Next, the example that you can give for this is multiplexer, adders, and counters. So as you keep moving down the line, the complexity of the circuit also increases, which means flip-flops are the basic memory element. Then you again go to the next level, which is mux. It is at a little higher level. When you go with microprocessors, it's still at a higher level, right? Then you go with 64-bit microprocessors. Now as you go down the line from 61, 66, 71, 80, so you will see that one major thing is happening. The number of gates are actually drastically increasing. So it started off with 20, and then it's moving on to more than 1 lakh gates, right? Now today's transistors or today's chips do have more than 1 billion transistors, which means they have billions and billions of transistors on a single IC. So all those ICs that you see, Intel i3, i5, i7, i9, so all these chips will have n number of transistors. Transistors numbers are not in 20s, it's not in 200s, it's not in thousands, it's not even in lakhs, but it is in billions. Okay, so that's the level of complexity actually increasing day by day. Now what is the advantage of having more number of transistors? Just recall the type of calculators that you had previously. We used to just have addition, subtraction, multiplication, and division, 4 major operations, that's it. But today's calculators, okay, if you can see, they do have a lot of operations. You can even do differentiation, integration, right? Many things can be done using your simple calculator. But just because the operations have increased, do you think the size of the calculator has increased? Not at all. It has in fact become more slimmer, right? So that is the advantage of having more number of gates on a single IC. Now moving on with the flow chart. Okay, many times this will be asked for your exam point of view. Okay, so this flow chart is important for your exam and for your tests. Okay, as to how is the design flow. So starting, you go with the requirements, then you see what are the specifications needed. It is just like, you're going to buy a computer. So before you buy a computer, you will decide, or you will think as to what should be my requirement. Then you will think, okay, how much GB of RAM should I need? How much hard disk should do I need to have, right? So all these things will come into picture. Then you will start thinking, okay, now along with this, what else can I combine, right? So starting off will be with the design specification. First will be requirement, then it will be your design specifications. Now after design specifications, then we come out with design formulation. Now what is this design formulation? Once we know that what is needed, okay, so we can actually we can actually think of how the design is to go, right? So which means once you have formulated the design, then you can think of what is going to be your design entry. Are you going to use VHDL or you're going to use Verilog? Okay, these things. Then once you write the code using your Xilinx, you'll be simulating them. Then you will check it for its logical synthesis. If it's not proper, now you can see a feedback here, right? You can see a feedback loop. So if the logical synthesis is not fine, you again go back and rework with your design, right? So the similar thing happens after simulation. You go back and work out with your design. So if everything is fine, then you keep coming down the line. So after logical synthesis, you will actually check your post synthesis simulation. So here what do? We actually check for, as I told you, once you have done your simulation and then later you want to make some changes or logical changes, okay, so that is called post means after synthesis. Now synthesis is after applying all this clock information, rise time, fall time, delay, all this stuff. So once we are clear with this, then we move on to the next section, which is nothing but your mapping, placement and routing. So here in this mapping, placement and routing, we will be rearranging things. So when I say rearranging things, those blocks which has more number of connections will be placed close to each other, and those blocks which do not have more connections will be actually placed far. Okay, so that is what we actually see in mapping, placement and routing. Okay, so here in mapping, placement and routing, you can see your FPGA programming unit, okay, and then your configured FPGA and ASIC mask. Now what is a mask? Mask is something where you will use for mass production, which means you have a mold. It is just like, while manufacturing soaps, the factories will have mold. So this mold is used for manufacturing n number of soaps. So similarly here, now you have a mask. Okay, so using that mask, you will be actually manufacturing your chip. Okay, so the image is actually burnt. Whatever image is there, that is burnt, and your IC is produced. Now here, okay, if you can see towards your right hand side, you will see schematic capture. Okay, now what is this schematic capture? It is nothing but it is the lowest level of abstraction. Now when I say the lowest level of abstraction, which means, now if I say I have a complex supercomputer, so do you think the supercomputer just came out like that? No, the basic elements is going to be your resistors, capacitors, inductors, all these things, right? So once we have them, then we start building circuits. then one circuit is actually merged with another circuit, making it a complex circuit, a hybrid circuit. So at the lower level of abstraction, at the lowest level, we have gates, flip-flops, and your standard building blocks. Now HDL, what is HDL? Higher level of abstraction. So this will have two parts, behavioral part and structural part. So in behavioral, you will be seeing your flow chart and algorithm. In structural part, you will be seeing your components or what kind of implementations that you will be doing. Okay. So here in behavioral model, okay, you see flowchart is available and your algorithm is available, right? So what do we do with flowchart? Why are flowcharts used? Flowchart is nothing but from the start what is going to happen. You have starting, so after that what is going to happen, next step. So it's a series of algorithms. So when I say flowchart and algorithm, they are actually connected to each other. So once you have a flowchart, you can actually write an algorithm. So flowchart will be the first step. Once you have the flowchart, then you can actually write the program, you can write the logic, right? Okay. Next, the explanation is about synthesis. Now in your exams they might ask about synthesis. What is synthesis? I've given you a lot of explanation on synthesis, and we're going to see the formal kind of explanation available now. Process of conversion of higher level abstraction of the design into actual components at the gate and flip-flop levels. So what is going to happen here? You're going to see a conversion from what? From higher level to what level? Flip-flop level. Now what is a flip-flop level? It is the lowest level. So you're actually converting a higher level abstraction to a lower level abstraction. The output of the synthesis tool is called the netlist. Now this is important. Okay. Now whatever output that you are getting from your synthesis tool, now who does the synthesis? It's actually done using your Xilinx. Okay, using your Xilinx. Once we connect your kit, your FPGA kit, okay, we can do the synthesis. We can even do synthesis using your higher level software, for example Cadence. Okay, even there the synthesis can be done at the software level, which is a list of gates and a list of interconnections. So netlist will have list of gates and interconnections. What are interconnections? Which block is connected to which block? How are the connections between block A and block B? So these are called interconnections. As the synthesis tool converts the design descriptions into hardware, it is also called design compiler or silicon compiler. So what is happening here? There is a conversion, there is a conversion that happens between the design abstractions. Now what is design abstraction? You have a higher abstraction level and then you have a lower abstraction level. So a conversion is happening from higher to lower. So that is nothing but called your synthesis. So on the whole, this process is called design compiler. Okay, so I hope you are clear with this point. Any doubts here? Can I proceed?
Yes, sir.
Yes. Okay, fine. So the only thing that you have to see here is the flow chart. Okay, and write a small explanation about it. What is requirement? Okay, what is simulation? These are main things here. Okay, what is mapping? What is placement? What is routing? Routing is connections between each block. Okay, fine. So the next one that we are going to see here is two scales. Okay, the one which is actually telling you the cost of design time and performance, and the other one is density and degree of customization. Now this is a very important graph where you actually compare different technologies as to how the complexity is increasing on one side and how much time it is taking for them to design. So this is involving your density, which is nothing but number of transistors on a chip, Then on the other scale, you have how much of design time. For example, for designing one chip, they might need about 40 engineer hours, or say 80 engineer hours. What is this engineer hours? 1 hour taken by an engineer to work on it, okay, productively. So you will be needing, that was just an example, 4080 which I told you, that was just an example. To design an IC, you will probably need up to 6 months, 1 year, okay. So there will be teams, okay, separate teams of engineers who will be working on specific tasks, okay. Just like how your OS is built, your operating system is built, just a single engineer will not work on the whole operating system. Some will be working on multitasking, some will be working on threads, right? Some will be working on IO, some will be working on the coding part. So many things, all these are combined together and made a single OS. So similarly here, okay, if you see the first one, okay, off the shelf gates, and then you have flip-flops. Off the shelf gates, whichever you can, which is easily available, okay, and gate or gate 7400, 7402, all this. So these are easily available, so the time taken for them, the design time is very less. So as you keep going forward, you have PALs, PLAs, PLDs, programmable array logic, programmable logic array, programmable logic device. Okay, so these are the three main differences. Then your complex CPLDs, okay, your PLDs, programmable logic devices, which are complex. Then FPGA. So as you see the ladder, it's just like a exponential curve that is increasing. So if you see custom IC, okay, the density and degree of customization is very high, which means you can customize it as per your wish, okay, and the time needed is also very high. But as you come down the ladder, for example, FPGA, which sits in between your custom IC and off-the-shelf chips, okay, it sits in between, so it finds a perfect spot between density and time taken, right? So here, if you see, you have uh, you have off-the-shelf flip-flops, okay, off-the-shelf gates, which doesn't have much density because it is just a single bit memory storage flip-flops, and the time taken is also too less. So this is how you should be able to understand the curve. Now here you should be able to remember a few of the commonly used abbreviations, okay. So I have put up all these things together here, okay. Especially during your viva, during your practicals, the most asked question is going to be VHDL. What is VHDL? Expand VHDL, okay. So it is actually VHSIC, hardware descriptive language. So HDL is hardware descriptive language, but V consists of VHSIC. What is VHSIC? Very high speed integrated circuit. So the full form of VHDL is going to be very high speed integrated circuit hardware descriptive language, VHDL, right? Next, CAD, computer aided design, EDA, electronic design automation, large scale, medium, small, very large, ultra large, ASCII, American Standard Code for Information Interchange. You have used this in your probably basic electronics, right? Basic electronics, and in your basic computer courses, you would have you would have come across ASCII codes, the keypads, the coding that happens for your keyboards uses ASCII. Then your ISO, ASIC, Application Specific Integrated Circuit, PLA, PAL, PLD, CPLD, STA, Static Timing Analysis. Right? So these are some of the common abbreviations that we'll be using throughout the course. So I've collected them all and put them together. Okay. So that's it I have for today's class. Okay. So few of the abbreviations. Okay. The flow chart, number of gates, okay, and certain bifurcations that happen between the ASIC technologies, and a broad overview of VLSI design and which companies are interested to hire you guys if you know HDL. Okay? So any doubts you can ask me right now. Any doubts?
No, sir.
Okay. And I have shared this material in the Google Classroom. Okay. You all can actually download it. Even yesterday's is also included with today's class. Okay. So you can download them and you can refer it. If in case you guys have any doubts, then we can have a discussion in tomorrow's class. Any changes in the class, I'll be informing you all beforehand. Okay. Is that okay with all of you?
Yes, sir.
Yeah, fine. Okay then. So probably we will conclude our class now. Okay, and we will probably meet in the next class with a new topic, and we will see as to how we will move forward with the programming point of view. We will see how exactly we can go ahead with using the concepts involved for your Verilog and VHDL. Okay, fine. Thank you one and all.